hello everyone, and welcome to our Festival of Landmark. Well, I suspect Llwyn Celyn will be very well known to many of you, but perhaps not at all to others. So before we hear from Danny, we thought we'd just give you a little bit of context on the site and explain the difference that the oxygen isotope technique made to the project team's understanding. First of all, the site's location. We are in the Clantoni Valley in Monmouthshire, just over the border between England and Wales. And you can see in the screenshot here the hand of the Black Mountain. So Black Mountain, so vividly described by the writer Raymond Williams. And here is Llwyn Celyn, just by the little village of Cymioe. Historically, this area was a tongue of English rule in the often fiercely contested marches. But today, Llwyn Celyn survives as a timber-framed house on an evolved site surrounded by its farm buildings. And it was in a state of extreme dereliction when Landmark was first called in 2006. It's fair to say that when we finally acquired the site in 2014, we were effectively buying a pig in a poke. The main house had been long swathed in this emergency scaffolding and sheeting, and it would be another couple of years before we saw it without its scaffolding. Except, of course, that it wasn't really a pig in a poke. The fact of Llwyn Celyn's existence and indeed its significance had long been known, and it was first surveyed by Fox and Raglan in their groundbreaking 1951 study, Houses of Monmouthshire. And this identified it as an extremely rare double hall house. So we have a hall here on the ground floor, but also an additional hall on in the upper part of the solar range that was built at the same time. And it was also described in Houses of the Welsh Countryside, as you see here, both books describing the house simply as late medieval. And we also knew it was special because of these exceptionally fine door heads. At the high end of the now sealed hall, it also still had a fixed bench and even the remains of a dais canopy, very, very rare survivals. And based on the style and weight of the timber frame, with its arched wind races and vestigial spear truss and the floor plan, we judged that Llwyn Celyn was probably built in the 15th century around 1480. And this reconstructive drawing was what we thought we had under the scaffolding as we reconstructed it when Landmark was setting out to raise the 4.2 million required to rescue and restore the site. A date of around 1480 was also plausible because Llwyn Celyn once stood on land belonging to Clantoni Priory, which you see here further up the valley. And in 1481, the Priory's daughter foundation, Clantoni Secunda in Gloucester, made a successful reverse takeover bid to absorb this original monastery in Wales. So that gave a plausible date for the construction of a new house. And in any case, we thought, hardly any vernacular buildings survive in Wales from before Owen Glyndwr's rising in the early 1400s, which left the countryside completely devastated. Of course, we were keen from the outset to try and find an exact date of construction. The house had previously been surveyed by the Royal Commission for Historical Monuments of Wales to assess its suitability for conventional tree ring analysis. But no suitable timbers were identified at that stage. And so, but nothing daunted, and with more of the building exposed, in 2016, we commissioned such conventional analysis from Dan Miles at the Oxford Dendrochronology Laboratory. That didn't yield a fix, so we were disappointed by that, but philosophical. Essentially, the timber was just all too fast grown to provide the distinctive ring width sequences for matching against the reference chronological database. It was, in the dendrochronologist's lovely word, too complacent as timber. In other words, it rained so much in the area historically that the trees grew happily and consistently without the signs of climate stress needed to calibrate a date simply from tree ring widths. We discussed the possibility of radiocarbon dating instead, but this is a much more expensive technique and typically, we felt, provides date spans that are too wide to add much to a building story. So there we left it. But then early in 2017, Richard Suggett of the RCHMW suggested that we submit samples from the timber cores already taken at Llwyn Celyn to the climate change team in the geography department at Swansea University. And they're working on the UK Oak project in a Leverhulme partnership with other specialists. And as Danny will explain, they are using a groundbreaking technique that relies on the chemical signature of oxygen isotopes in tree rings to date the timber samples. Two of the existing Llwyn Celyn cores with intact sapwood and bark edge were identified as the most suitable for analysis. And as this was the first time that this experimental technique had been used on a building of unknown date, the project team asked Landmark to commission parallel radiocarbon analysis as independent validation. And thanks to our Heritage Lottery funding, we were able to afford and agree to this. So Neil, Danny and the Swansea team then disappeared into their labs for the next couple of months. And then came the bombshell. You don't have to be a scientist to understand how our jaws dropped and we just gasped in delight when we saw this deceptively simple graph of their results. Just look at the date on that spike, 1420. The analysis was giving statistically robust results for a felling date of winter 1418-19 for a principal rafter in the solar roof, and winter 1420-21 for a joist at the service end, which is what this graph shows. Both sampled timbers are unequivocally in their primary build positions. And as further validation and delight, the parallel radiocarbon dating yielded an unexpectedly narrow range of 1407 to 1428, so validating the accuracy of this first ever application of isotopic analysis to an undated building. So these results allow us to say with confidence that the main house at Llwyn Celyn was built in 1420. Now, a date of a mere 60 years before our earlier informed guess of 1481 might not seem terribly exciting given the span of the centuries, but this is where historical context comes in. Because 1420 is intriguingly early in the period of reconstruction that followed Owen Glendower's rising. Clantoni Priory was sacked by Glendower's men in 1405-6, and it was a period of wholesale destruction by both sides in this conflict. Hardly any houses were left standing. So this timber dating had identified Llwyn Celyn as one of the oldest surviving domestic buildings in Wales and completely transformed our understanding of its history. It was not a Gloucester Prior's new residence from the 1480s, but rather a high status house built when the fires of the Glendower Rising were barely quenched. So having set that project context, I'll now hand over to Danny to explain how he and the team pulled off such a coup.
Thank you very much, Caroline. I must say it's rather odd to be giving a talk on dating old houses because I'm really a climate scientist. And before we dated Llwyn Celyn, I must admit I knew absolutely nothing at all about old houses. The idea of a whole house was completely new to me. So I'll try and tell the story of how we got to that point. So it's not just me, of course. We've got a big team in Swansea, and we also work with colleagues in Oxford. You've already heard of Dan Miles. So the technique works with oxygen isotopes. So I thought I should begin by just explaining what they are. And there's actually 3 different types of oxygen in the air around us. The most common one is called oxygen 16. And there are 2 others that are a little bit heavier, oxygen 17 and oxygen 18. And the only difference is the number of neutrons in the nucleus. And what it means is that oxygen 18 is a little bit heavier. And this actually has implications for the way that it behaves. It doesn't matter to us. If we breathe oxygen 16 or oxygen 18, we wouldn't notice a difference. But if you've got water that contains oxygen 16, the molecule is a little bit lighter than a molecule that contains oxygen 18. And so if you've got evaporation, the lighter water is more likely to evaporate. And when you've got clouds, the heavier water is more likely to drop out. And so this ratio of heavy to light oxygen, usually in water, is used in all sorts of branches of climate change science. It's the main thing we use in ice cores, for example, and also in deep sea sediments. And this is why we know that there have been many ice ages, for example. And we can measure the same thing in tree rings. Tree rings consist mainly of carbon, oxygen, and hydrogen. And all 3 have isotopes that we can use. And in Swansea, that's what we specialize in, mainly oxygen and carbon. And for years, we worked in very remote places. And Caroline mentioned the fact that trees in Wales are very happy. There's no real climate control on growth. So like everyone else who works with trees, we initially worked in quite remote places where the trees are really under pressure from climate, and then they respond to the climate. So for years, we worked up in the very far north of, this is the far north of Norway, Sweden, Finland, and even into Russia. And we worked with people looking at ring widths and various other measures. And that's when we learned to work with oxygen and carbon isotopes in tree rings. And Neil in particular, Neil Loader, developed lots of techniques to make the process more rapid. But the downside was always that we were reconstructing climate of places where very few people have lived. And we always thought it would be much nicer to reconstruct the climate of somewhere like the UK. So this is the team this is in northern Finland. This is Neil Loader in the middle here. This is Ian Robertson and Mary Gajan. And we worked almost exclusively on pine trees. And pine is quite easy to work with. It has quite nice, clear rings. You can use the whole ring. The wood is quite soft. But we thought it really would be nice to reconstruct the climate of the UK, and particularly Wales. So here's a little quote from the Swansea poet, Dylan Thomas. "Some let me make you of the bowled beeches, some of the oaken voices." And this was the real challenge to us. Could we change from working with pine to working with oak? And could we really extract a climate signal from somewhere that's just warm and wet all the time? And this is something that nobody has achieved. There are no good tree ring reconstructions of climate for anywhere in the moist mid-latitudes. There are some reconstructions, but they're really very, very weak. But with oxygen isotopes, we have a chance. And that's because of where Britain lies. Britain lies in a bit of a sweet spot in terms of oxygen isotopes in rainfall, because the ratio of the heavy to the light oxygen in rain is dictated by the sort of air circulation that's happening. And there's a very big difference between a wet summer and a dry summer. And it's caused by the position of the jet stream. So on the left here, we have, it says here a normal summer. I don't know who wrote that, but a good summer in Wales. The jet stream is to the north. And we have warm air from the south. And we have thunderstorms. And thunderstorms have very characteristic signatures of oxygen isotope ratios. And then in a miserable year, this past August, for example, the jet stream was too far south. And then we just get front after front after front. And we have very different, very low isotope ratios. And the trees don't care. The trees use whatever water they can get. So we wondered whether it was possible that oak trees would pick up this signal and that it wouldn't matter that they weren't stressed. And in fact, it might actually be an advantage not having any climatic stress. The trees might act as a sort of passive monitor of this natural signal. And when the jet stream is to the south, our winters are much, much wetter. Sorry, summers are much, much wetter than when the jet stream is to the north. So we predicted from first principles that we would get a signal in oxygen isotopes that was related in some way to the amount of rainfall in the summer. But oak is a very difficult wood to work with. So this is a section through a piece of oak. And it's very pretty oak. This is the heartwood-sapwood boundary over here. But this is a ring of oak. And oak looks so nice because every ring actually has two bits to it. So this lighter coloured bit with the big holes is what's called the early wood. And this dark bit is called the late wood. And that's a single ring, that pair. And what happens with a pine tree is in the spring, the pine tree wakes up and it immediately starts to make wood. But the leaves are already there. So it gathers energy from the sun and it makes wood using the sugars that are formed in that year. But oak doesn't do that. Oak works in quite a different way. And it's because of the way they transport water. So what happens with an oak tree is in the spring, if you notice in the spring, oak doesn't open its leaves when the other trees do. Most of the trees open their leaves and the oak is still bare. But actually it's not sleeping still. It's actually making this layer of early wood. And that's because it needs these big cells to transport water to the leaves, to allow them to open and flush. And these big cells get damaged in the winter by frost. So it's essential for oaks that they make this layer of wood before they open their leaves. And this is really bad for climate reconstruction because it means that that wood is made from some stored material from previous years. It doesn't represent the same year that the ring was formed. So what we need is this later bit, this dark bit, and that's called the late wood or the summer wood. And that forms in the summer after the leaves have opened. And that represents the climate of the current year. The problem is that oak trees desperately need to make early wood, and that's what allows them to function. They don't really need to make late wood. They need some late wood to make them strong. But if they've had a tight year where they're not doing very well, they can just skip it. And that's what we see on this lower one here. At the start, the tree is growing very well, nice big thick rings, plenty of late wood. But then we see a growth decline, and then many years with just every band of circles here is a ring. So there's no late wood at all. So there is nothing here to measure for us. So oak is very challenging to work with. But over the years, we have perfected a method now that allows us to do it. So I'll just run through briefly what we do. First of all, we take cores. You saw a couple of examples in Caroline's slides. And the first thing is to make a thin section of wood, about 1 millimeter thick. And to do that, you have to glue it onto a piece of softwood, and then you polish it very carefully. This is really skilled work. This is done by our colleague Dan in Oxford. And he also counts the rings and he marks them in decades for us. Then the next thing we do is we very carefully, under a microscope, slice off just the late wood. So we don't use the early wood at all. And the late wood is sliced into really thin slivers. And we have extremely skilled technicians to do this, Gareth and Darren. If you make a mistake here, everything else is a waste of time. So it's very, very careful, skilled work. And then what we want is the cell walls that formed in the summer and nothing else. So we don't want any of the lignin that comes later to make the wood strong. We don't want any of the chemicals that move between the rings along the rays. We just want the cell wall that formed in the summer. So we've got a series of chemical steps that Neil has perfected. And we end up with a tiny amount of fluff. It looks like cotton wool. And that's what we need. That represents the summer that ring was formed. And then we measure the ratios of heavy to light oxygen. And I've just put a scales on here because an isotope ratio mass spectrometer is not very photogenic. It's a big white box. But effectively, it is a weighing scales. It measures this ratio relative to a standard. And oxygen 18 is a little bit heavier than oxygen 16. So that's how it works. And we tried this using some trees initially from West Wales. It was one of our ex-students suggested that we try this. I was very skeptical, but he suggested a set of trees near Lampeter in West Wales, really wet, miserable place. Well, Lampeter is probably very nice, but the climate's not very good. And we added in a few sites from here and there that we just had wood. And we got this most amazing result. I was used to working in northern Finland, northern Norway. The climate signal that we got from these trees in the UK was as strong or stronger than the signal in pine trees growing right at the limit of pine growth. It's the most amazing result I've seen in my whole career. And the most amazing thing was that we measured the carbon and the oxygen isotopes. And we do it automatically on the same burn in the machine. And the carbon correlated with summer temperature. And the oxygen correlated with summer rainfall. It was really quite amazing. So on the top one here, the orange is the measured temperature, thermometers, and the red is the carbon isotope signal. And on the bottom, the light blue is measured rainfall, summer rain, and the dark blue is the oxygen isotopes. So we thought, this is fantastic. All we need is some old oak, which we knew we could get from the dendrochronologists, and we could reconstruct summer temperature and summer rainfall for maybe 1,000 years. We thought, we'll definitely get a grant to do this work. So we applied to the main funder of climate change research, the Natural Environment Research Council. But they're notoriously scared of risk. They say they're not, but they really are terrified of risk. And we applied and we said, we think this will work. And the reviewer said, well, it might work, but I'm not really sure. So they said no. So we applied again and they said, well, it might work, but we're not really sure. And in the end, we applied 4 times. And they just wouldn't take the risk. So we thought, what can we do? Because we were sure it would work. And we thought, well, what about the Leverhulme Trust? And the Leverhulme Trust are really a fantastic funding agency because they do have a reputation for taking risk. And in particular, what they'll do is they'll look at the person who's applying for the money and they'll say, has this person done well in the past? Okay, if that's the case, if they want to work on something new, something unproven, we'll give them a go. So we thought Leverhulme might be the way to go. But the problem was they don't fund failed applications to other grant bodies. They're not a funder of last resort. They want to fund something new and exciting. So we didn't really want to apply to do the same thing. So we thought about this and we thought, well, we'd always known that if we did have an 800-year, say, reconstruction of oxygen isotopes, we would definitely be able to use that to date old buildings. And actually, everyone who works with isotopes in tree rings knew that. But nobody could afford to do it because you would need to measure every year for 800 years. And from several, not just 1 or 2, several different timbers in order to have something to date against. Because if you take a timber from a building, you have to have something to compare it to. So nobody could afford to do this. But we realized we were in a position where we'd spent years developing methods to make the isotope measurements more rapid. And we had a secret weapon, which is Dan Miles, who you've already heard about. And Dan Miles is a very well-known expert in dating old buildings. But also, he lives in a cottage. The cottage is actually older than Clantoni. It's in Oxfordshire. And underneath the cottage, he's built himself an office. It's like the Bat Cave. And every building, every timber he's ever dated, he's kept. And they're all archived in this wonderful office. So we didn't have to go back to any buildings. We didn't have to spend any money on sampling. We could just go to Dan and say, Dan, have you got something from 1300 to 1340? And he would just give us a list. And also, he works closely with Christopher Bronk-Ramsey, who runs the radiocarbon lab and is the top expert in the world on statistics of dating. So we had this really good interdisciplinary team. So the Swansea team, who knew a lot about isotopes in tree rings, nothing about old houses, nothing about dating. And then Dan, who is a real expert in old houses and in dating, and Christopher with his statistical expertise. So when we went to Leverhulme, they funded us. And I knew nothing at all about old buildings. So Dan would send through these lists of cores that he had. So we would say, can we have something from 1610? And he would come back with, we have bad 18. And eventually we got a list of what these meant. And actually, it turns out that all these codes relate to these wonderful old buildings. This is one that we've used quite a lot, Baddesley Clinton in Warwickshire. There's several phases rebuilding, and we've got lots of samples from there. Well, this is Anne Hathaway's cottage. I think probably wasn't Anne Hathaway's cottage, but we've got some samples from there, and lots of others, several cathedrals, lots of churches. So fantastic resource that made the work possible. And this is the white dots here are the source of the timbers that Dan provided. And this is what we produced. And the record goes from 1200 to 2000. The last bit's missing here, I'm not sure why. And what we did was we took, for every single year, individual year, we took the late wood only from 10 different building timbers, spread over an area as large as possible from central England. And then for each year, we put 5 timbers in one cup and 5 timbers in the other. And then we did the chemistry on a group of 5, and that was to lower the costs. And so we've got 2 independent chronologies. So in total, 8,000 rings sampled and polished and cut individually. So a huge, huge amount of work. And until we'd done this, it wasn't possible to date anything. And it was just at this stage that the Landmark Trust got in touch. And at this stage, we were just testing the method. And we did that by Dan would pick a sample where he knew the date, but he wouldn't tell us the date. And then we would date it. And then he would tell us if we were right. And I must say, although to be honest, I wasn't interested in dating old buildings. I just wanted to do the climate work. But now it started to get quite exciting, because when you write a grant proposal, of course, you're full of enthusiasm and you say how wonderful the method is going to be. And we thought it would work, but we had no idea how well it would work. It was completely beyond our expectations. The dating is extremely strong. And every sample that Dan gave us, we were able to date. And this is the point where Dan said, well, why don't you have a go at this one? I have no idea what the date is. And that was the only sample at that stage that we touched, where we had no idea. And this is what we had to work with. So this is one of the 2 samples. And you can see here, in total, it's got 50 rings. But that includes this bit near the pith, that the tree would have been, you know, as thick as a brush handle. And then at the end, we've got some worm-eaten wood that we can't really work with. So not very many rings. And also, look how complacent. Every ring looks much the same as the other. And this is absolutely hopeless for traditional dendrochronology. These trees are much, much too happy. But actually, it was easy to cut, and there was plenty of late wood. And they dated beautifully. And here's the result. And this is the bit that I actually do. I don't do any of the chemistry or cutting, but I do the statistics of actually finding the date. And I won't go over it now, but I can answer questions if you're interested. But this is the fit down here between the master chronology in grey, and the red one is the sample. And here's the date of 1420. I must say it was, Caroline was very excited about the date. And I remember she sent an email saying, "You mustn't tell anyone this date." And this caused howls of laughter in Swansea because we had no idea that this date was important. For us, 1420, 1480, 1580, it didn't really matter. We were just interested in the statistics. But it was a very strong date. This is the important graph here. This is the chances of it being wrong. So if you were to try to date another timber, the chances of getting such a good match just by luck would be less than 1 in 10,000. And that the match at 1420 here is more than 1,000 times stronger than any other match. So it was already a very strong date. But Dan in particular was very keen that we should apply a very strict sort of belt and braces approach. And we really had to get the date right because it was an important date. And that's where the support of the trust in providing the radiocarbon was really critical. And here's the radiocarbon result. I won't go over this in detail, it's quite technical. But Caroline said that with radiocarbon, you often get a big margin for error. And we haven't got a big margin for error here. We've got actually a tiny margin for error. And that's not a mistake, and it's not by luck. It's because we already knew the answer. We already knew the date. And so we could pick the rings for radiocarbon that, if we were right, would give the smallest error. And Neil did that, and that's why it works so well. So I thought that was it. See, Dan had said, "Can you date this old house in Wales?" And we said, well, we can try. But then I made the mistake of visiting Llwyn Celyn, and it was still in a terrible state at the time. And they were very kind. They showed me around, the people who were working on it. And I remember thinking, why are you trying to date it? It's going to fall down on you. It really looked as if it was beyond saving. But and then I went back several times, and on one occasion met Richard Suggett from the Royal Commission. And then I really, was told how important the house was. And then I did some reading. And if you have a chance to read, this is a book that Richard wrote about houses in Radnorshire. And it really brought it home to me that this isn't just dating wood. This is dating a piece of living history. This is a house that has been standing in that landscape, and people have lived in it continuously until the trust rescued it. And then also we started to work with Caroline, and she was the one that explained that if you know the date of something, for example, if you know when that fireplace was inserted, you can say who did it. The historians can find out who was living in the house at that time. How many children did they have? When did they inherit? And you can go to the local graveyard and they're there. They're actually there in the graveyard. So Swansea team were completely hooked now. Although we knew nothing at all about old houses, we were completely hooked on Llwyn Celyn. And the final nail in the coffin for us was the trust actually let us stay in Llwyn Celyn for a midweek break. And so we pulled out all the stops and we tried to date everything that we could. So we dated some of these inserted, this is a floor inserted in the old hall. And we tried to date that mantle beam and all the outbuildings that we could access. And it was extremely challenging work, actually. And really a fantastic project for us because we learned so much. And the wood was terribly, terribly difficult to work with. This is actually the mantle beam at the bottom here. And what you can see is that there are periods of rapid growth with great big rings. And then there are periods like here where there actually isn't any late wood at all. Growth has almost stopped. And then huge growth again. And here, just repeated growth stop and release. And this is a close-up of one of those events. And what we can see here is very rapid growth. And then the tree stops growing. It just makes early wood. And then the whole thing starts again. So there are 10 rings in here, but we can only see 3 really. So very challenging to deal with. And we had to rewrite all our software to cope with this. But in the end, everything did date. So every timber that we tried to date, we did manage to date. Even the mantle beam, this is the mantle beam here with just these bits and pieces of rings that we could actually measure. And these are the dates. So there's the original building date. And then they built the beast house before they put the floor in. And Richard Suggett was able to explain why this was. Cattle were very important in the economy. You had to look after your main source of wealth. And then apparently the date for adding the floor and the chimney was extremely late. Caroline explained this, and she was able to say who owned the house and why they had the money to do this. And then eventually this date of 1843 at the end was for a cart shed. And actually that turned out to be very important for us in Swansea. And in the end, we were actually able to do our climate reconstruction because we had the money from Leverhulme to do the dating chronology. We were able to use that to reconstruct the climate. And then NERC did give us the money to do the work. Once we'd already done it, they were happy. And this is the climate reconstruction, which we've just published. This is the first part of it. And then now we're working with historians of climate to check that we've got the drought years correct and the wet years and so on. That's open access. You can have a look. So what do we do next? Well, we're hooked on dating old buildings now in Swansea. So Caroline's asked us to date Calverley Old Hall in Leeds, which looks very beautiful, so we'll do our best. We've got students who are very keen to work with us. So one of the girls was from Abergavenny, so she's had a go at dating the old tithe barn. I won't steal her thunder, she'll release her own date. And now we just want to keep pushing back. We've got back to about 800 AD now, but I would like to carry on working backwards now. So we're working on some Roman material and some Iron Age material, but the potential is there to go back for 10,000 years. And that's what I would really like to do. There we are. Thank you very much.
That's absolutely brilliant, Danny. I defy anybody who's listening not to wish that they couldn't have a parallel career now as a climate change scientist. Fantastically sort of clear explanation. I'm just going to quickly swap screens again for a last couple of slides to just elucidate a tiny bit on what Danny was saying about the evolution of the site. So, because it really was transformative from our point of view, not just for the main house. Danny's explained how the house was sealed over in the 1690s. And meanwhile, in parallel, there had been documentary research going on as best we could to try and untease who'd lived in the house when. The main 1420s house stood, as we see, unchanged for almost, or for more than 200 years, in fact. And so it was still an open hall house in 1656, when its lease passed to the Watkins family. By then it would have been outdated and by implication rather run down as an open hall house. And the Watkins brought a new injection of energy and funds. So it's them who put a ceiling into this main hall, insert the enormous chimney stack, and also add a rear kitchen, which would be here if it were shown on the reconstruction drawing. And so the work allowed us essentially to date the buildings on the entire site that you see here. We have the main house, 1420, in the middle, as well as the changes that, or predating the changes that actually happened in the main house. We have the construction of the Beast House, as Danny explained, which is this building here. Also the rear kitchen, out of sight behind this range. And then also this little tiny link house, which is here. Now, we wish we'd had the dating work earlier in the project, with hindsight, in fact, because what this proved was that this little link house must post-date the threshing barn, or just, you know, just post-date, because it's keyed into the threshing barn. And whereas the threshing barn we had thought was 18th century, it emerges instead as being probably late 17th century instead. And yes, you then see the yellow blocks, the 19th and 20th century editions. This little lower barn, also very important in terms of the dating sequence. So the whole site really was informed by the work that Danny and Neil and Dan and the others did. And I can't resist giving you just a glimpse of the finally restored interiors to remind you what the point of all this was ultimately, which was to rescue and restore this amazing house and make it available to everybody for holidays. So as the collaboration, as we've seen, you know, the collaboration between Landmark and the Oak Project at Llwyn Celyn has witnessed a major step forward in the timber dating of historic buildings, as well as yielding significant insights into Llwyn Celyn's history. And as Danny says, we just very much look forward to working together just as fruitfully on other projects.